take about 5. Hard to follow a person's notes sometimes. So, when you have a t here, we realize that this makes this negative squared x of s minus, now normally it would be s x naught minus x prime naught. Okay? And then the whole thing, take the derivative of the whole thing with respect to s. Notice this part doesn't have an s, so it's going to go anyways. And here in this problem, we're told that x naught is 0. So, it really just becomes this thing here. Plus, oops, it's not going to be plus, it's going to be minus 3. Okay, and then again, this is going to be s x of s prime minus s x of s plus 3x of s equals 0. Take the derivative here. See if I can do it right this time. It should be negative 2s x of s. This is a product rule. Same thing here. So, if you pull out all of the x primes, these two here, you're going to get s squared minus 3s, or plus 3s rather. Take a negative out. Okay. Okay, now if you count the other ones, you see these are s's here, so negative 3s, negative 3s of them. And then these two cancel out. So minus 3s x of s. And again, let's lose the, well, I feel like again, it's probably the first time I said it this time on this video. You have this. Now what you see is this is a separable differential equation, because this is really like this, really is what this is. So if you do this, you get 1 over x dx. And over here you're going to get negative 3s squared plus 3s ds. Okay. Bring up the calculator. That negative 3 ln of z, or in other words, ln of s plus 3 to the minus 3 is equal to the ln of x. Okay, of course, there's plus ln of some constant too, I guess. Okay, raise both sides to the e, you end up with e is equal to, this is a product. This ends up going to go on the bottom, so it's going to end up being the c over s plus 3 cubed. Okay, this is, oops, x as a function of s. That's what that is. Now, in a second, we're going to see if we can figure out what that is when we do the inverse. Okay, so here we have that. Now the question is, what is that thing? If you're looking at it in terms of a inverse Laplace transform, because that's what we've got ourselves down to the point of we need to find just what is that thing. So if you look back on page, for goodness sakes, yeah, back on page right, 446. Yeah, so that thing actually comes out to be, if it was 1 over c plus 3, it would be e to the minus 3t. if it was that squared, it would be t squared e to the minus 3t. But because it's cubed, it ends up being t squared e to the minus 3t. So, again, now I've lost my pen. There it is. Now, because it is in this format, this s plus 3 in the bottom is e to the minus 3t. We know that. Again, if it was squared, it would be t squared here in front. It would be t, I mean, so because it's to the third, it's t squared. And now, in reality, what we have here is we have a repeated root, basically, is what we're saying here. And then a constant times that mess. This is x as a function of t. Well, look at that. 5th time's a charm. On the 5th try, I was able to make a video that actually made sense start to finish. Alright, let's set up another one. Another example. See if I can do this one right off the bat. Shouldn't be that hard when you have notes, but sometimes it is. This problem started out to be 2t minus 1 x prime, but I FOILed it out, so it's a little easier to work with. So it's minus parentheses s squared. Again, same thing as last time. X naught is 0, and x prime we don't know, but we don't worry about it because it has no s involved. Here it's minus 2s x of s prime minus 2s x of s minus 2x equals 0. Jiminy Christmas. Oops, this should be 2x of s. Okay. That said, if you collect your like terms, that's s squared plus 2s x prime of s. And if you collect all your x's, you should end up with 4s plus 4 x of s's again. Again, that is separable. And so what you end up with is just exactly what you think. So I get 1 over x of s dx. Like that. That thing, because they're both squared, so it's oops, and oh, it's negative. That would be helpful too. That'd be nice to know. So if I put a negative back in here, right there, they end up both being negative this time, which is what it's supposed to be. Okay. And so when you redo this, then you get 1 over, or you get the ln over here and ln's over here. They're both on the bottom though, because of the negatives. So what you end up with is x of s is equal to s squared, and then s plus 2 squared. The constant on the top. Now what you can do. Alright, and so x of s is this thing right here, and if we go back to the 89 and we type it in just like that, except we do expand, and again we should put a variable on top for a constant, and what you're going to see is when we do that, Anyways, going to blow it up into 1,000 pieces, all of which have a y over 4 involved in them. So that's a constant. So you get a constant over s plus 2, which is e to the minus 2. So, coming out here somewhere, I'm just going to write e to the minus 2 t. And then a constant in front of that. They all have the same constant if you look. And here you've got s plus 2 squared, so that's plus t e to the tu minus 2t. And then, oops, here you've got 1 over s, so that's just plus, just a minute. Sorry about that, take a phone call. And then, see this constant over s, that's of course just 1, so it's minus 1, again, times the constant here. And then the last one, of course, is over z squared, which is t, so plus t. And this is our function, x is a function of t now. Okay? So that's basically the gist of the hardest part, honestly. The hardest part is making sure you collect your like terms. You have no idea, if I wasn't so embarrassing of my algebra, I would show you the piles of papers this weekend that when I was sitting down trying to make up some notes, that I would add funny somewhere, or oh, you left an S off of one of them. Kind of a giant pain in the butt, but there they are.